The next question deals with predicting the shape of the molecule. I will read the question for you. Which of the following pairs are isostructural? Which of the following pairs have same shape? Your options are option A, NH4 plus and NH3, option B, CH4 and BF4 minus, option C, NH2 minus and BEF2, option D, PCl3 and BF3. To predict the shape, first you need to predict the hybridization, find the number of bond pairs and lone pairs, and then we need to predict the shape of the molecule. So we'll just check for first option A, which the pairs are NH4 plus and NH3. To determine the shape of the molecule, first you need to find the hybridization, and you know how to find the hybridization. We generally use the formula hybridization H is equal to half of valence electrons that are present with central atom. Here the central atom is nitrogen 5 plus the number of monovalent atoms plus 4 minus the charge present on the cation. It carries the charge of plus 1 and minus 1, anionic 0. So 5 plus 4 minus 1, 8 by 2, that will be equal to 4. 4 indicates the hybridization is sp3. If the hybridization is sp3, then the molecule contains 4 orbitals. In NH4, nitrogen is linked to 4 hydrogen. That means all the 4 positions are occupied by hydrogen. Hence, the shape of NH4 plus is tetrahedral. It has a perfect tetrahedral shape, where the 4 positions are occupied by the hydrogen. Let us check for the shape of NH3, and we'll just compare. If they have same shape, then option A will be the right answer. Hybridization of nitrogen here, H is equal to half of valence electrons present with nitrogen plus the number of monovalent atoms 3. It does not carry any charge, so plus 0 minus 0. So the value will be equal to 4. 4 indicates the hybridization of nitrogen is sp3 here. If the hybridization is sp3, then the geometry will be tetrahedral. But nitrogen is linked to 3 hydrogen. That means nitrogen contains 3 bond pairs and 1 lone pair. That is, in ammonia, since the hybridization is sp3, the geometry should be tetrahedral. But this contains 3 bond pairs and 1 lone pair. So out of the 4 position, 1 position will be occupied by lone pair and the 3 positions will be occupied by bond pair. Hence, NH3 has pyramidal shape, whereas the NH4 plus has tetrahedral shape. Hence, option A is not the right answer. Let's check for option B. Option B, we have methane and we have BF4 minus. If we calculate the hybridization of carbon in methane by using the formula, the hybridization of carbon will be sp3. sp3 indicates it contains 4 hybrid orbitals. Carbon is linked to 4 hydrogen. That means carbon contains 4 bond pairs and it doesn't contain any lone pair. That means all the 4 positions in carbon are occupied by hydrogen only. Hence, methane has a tetrahedral shape. Let's check for BF4 minus. If you find the hybridization of BF4 minus, the hybridization of BF4 minus, boron in BF4 minus is sp3, because it is half of valence electron present with boron. Boron contains 3 valence electron plus 4, 7 minus 1, that means negative charge, you should add it. It will be 8 by 2, it will be sp3 hybridization. Boron is linked to 4 fluorine. That means all the 4 positions of boron are occupied by fluorine only. Hence, in BF4 minus, all the 4 positions are occupied by fluorine. Methane has sp3 hybridization. In methane, carbon has sp3. In BF4 minus, boron has sp3. Methane contains 4 bond pairs. In BF4 also contains 4 bond pairs. Hence, methane has a tetrahedral shape and BF4 minus also has a tetrahedral shape. Hence, option B is the right answer. The next question deals with predicting the bond angles. The angle between the covalent bond is maximum in option A CH4, option B NH3, option C H2O, option D BF3. The basic information regarding the bond angle can be obtained from the hybridization itself. If the hybridization is sp, the bond angles will be around, if the central atom has sp hybridization, the bond angles will be 180 degree. If the hybridization is sp2, the bond angle will be 120 degree. If it is sp3, it will be 109 degree 28 minutes. If the hybridization is sp3d, then the bond angles will be 120 degree and 90 degrees. If the hybridization is sp3d2, then the bond angles will be 90 degrees. If two or more molecules have same hybridization, then the bond angles can be predicted based on the number of lone pairs of electrons that are present. As the number of lone pairs of electron increases, the bond angle decreases. Let us solve this problem. Option A is methane. First you need to find the hybridization of methane. Hybridization, the number of hybrid orbitals, half of number of valence electrons that are present with carbon, 4 plus 4. It doesn't carry any charge, so it is C, and A value will be 0. So the value will be equal to 4. 4 indicates the hybridization is sp3. Carbon has sp3 hybridization, and carbon is linked to 4 hydrogen atoms. That means out of 4 orbitals that are present with carbon, all the 4 orbitals are occupied by hydrogen. Hence, methane has a tetrahedral shape with a bond angle of 109 degree 28 minutes. Let's move on to NH3. Hybridization of nitrogen in NH3, H is equal to half of valence electrons present with nitrogen 5 plus the number of monovalent atoms. It does not carry any charge, so minus 0 plus 0, so the value will be equal to 4. 4 indicates the hybridization is sp3. If the hybridization is sp3, then nitrogen contains 4 sp3 hybrid orbitals. Nitrogen is linked to 3 hydrogen. That means out of 4 orbitals, 3 are occupied by hydrogen and 1 is occupied by a lone pair of electron. Since the hybridization is sp3, the geometry will be tetrahedral, but one position will be occupied by lone pair and 3 positions will be occupied by bond pair. Due to lone pair of electron, the bond angle decreases. Why? Because lone pair provides repulsion to the bond pairs. As a result, the bond angle in ammonia will be less than 109 degree 28 minutes. Let's move on with water. If you find the hybridization of oxygen, the hybridization will be sp3, same method. sp3 hybridization indicates oxygen contains 4 orbitals, but oxygen is linked to 2 hydrogen. That means out of 4 orbitals, 2 are occupied by hydrogen and 2 contains lone pair of electron. As a result, the shape will be a bend shape. In water, the bond angle will be less than the bond angles that are in ammonia. Why? Because ammonia contains 1 lone pair and nitrogen contains 1 lone pair. In water, oxygen contains 2 lone pairs. The lone pair repulsions are high as compared to the lone pair bond pair repulsion. Hence, the bond angle will be less as compared to the bond angle in ammonia. Let us check for boron trifluoride. Boron trifluoride, the hybridization of boron will be sp2. You can calculate by using the same formula. The hybridization will be sp2. sp2 indicates boron contains 3 orbitals and all the 3 orbitals are occupied by fluorine. Since the hybridization is sp2, the geometry should be trigonal planar, and since all the 3 positions are occupied by fluorine, the molecule will have a trigonal planar shape with a bond angle of perfect 120 degrees. Now we can compare. Methane, the bond angle is 109 degrees. Ammonia, the bond angle is less than 109 degree 28 minutes. Methane, perfect 109 degree 28 minutes. Ammonia, the bond angles are less than 109 degree 28 minutes because of the presence of lone pair of electron. In water, the bond angle is less than 109 degree because it contains two lone pair of electron. Boron trifluoride, the bond angle is 120 degrees because it contains a trigonal planar shape. The question is, the angle between the covalent bond is maximum in boron trifluoride, and hence boron trifluoride is the right answer. Covalent bonds can be classified into polar and non-polar bonds. If the bond is present between two atoms with similar electronegativities, then the shared pair of electron will remain exactly at the center and there will be no charge separation. If a covalent bond is present between the two atoms with different electronegativities, then the shared pair of electron moves towards the more electronegative atom, hence there will be a charge separation. If there is a charge separation taking place, as in the case of HCl, in HCl, chlorine is more electronegative than hydrogen. As a result, chlorine will acquire a slight negative charge and hydrogen will acquire a slight positive charge. If there is a charge separation taking place, then such molecules are referred as polar molecules, and since the bond is polar in nature. If the bond is present between the two atoms with similar electronegativities like hydrogen, then the shared pair of electron will remain exactly at the center. Then such bonds are referred as non-polar bonds, and the molecules can be referred as a non-polar molecule. This polarity is measured in terms of dipole moment. Dipole moment is defined as it is the product of charge and distance between the two charges. For diatomic molecules, dipole moment depends upon electronegativity. As the electronegativity increases, dipole moment also increases. For example, if we take an example of HCl and HF, out of chlorine and fluorine, fluorine is more electronegative than chlorine. As a result, there will be more charge separation here. Hence, the dipole moment of HF will be greater than the dipole moment of HCl. In the case of polyatomic molecule, dipole moment depends upon the shape. For example, water has a bent shape. Its dipole moment is not equal to 0, whereas BeCl2 is linear and its dipole moment is equal to 0. Because in BeCl2, the two bond dipoles are equal and opposite, hence they cancel each other, hence the resultant dipole will be 0. So in the case of polyatomic molecule, so dipole moment is sum of all the bond dipoles. If we take an example of boron trifluoride, in boron trifluoride, the resultant of these two dipole will be equal and opposite to the third dipole. Hence, boron trifluoride, the resultant dipole will be 0. Now the question arises, how to find the dipole moment or how to predict whether the given molecule has 0 dipole or a non-zero dipole. Molecules with regular or symmetrical shape, I mean if the molecule is linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, square planar, that is if it is symmetric and if all the side atoms attached to it are same, then those molecules have 0 dipole and the molecules are referred as non-polar. Molecules with irregular shape like bent, seesaw, trigonal pyramidal, square pyramidal, these molecules have non-zero dipoles and the molecules are polar in nature. The next question is, which of the following has non-zero dipole? We need to first predict the hybridization, then you need to find the shape of the molecule. If the molecule have symmetrical shapes, then that molecule will have a 0 dipole. If the molecule has irregular geometry or unsymmetrical shape, then that molecule will have a non-zero dipole. We'll take with the first option, option A, boron trifluoride. To predict the shape, first we need to find the hybridization, which we have discussed. Hybridization is given by the formula half of valence electron present with boron. Boron atomic number is 5, hence it contains 3 valence electrons plus the number of monovalent atoms that are linked. Fluorine is a monovalent atom, so 3 monovalent atoms are linked plus 3. It does not carry any charge, so plus 0 minus 0, so the value will be equal to 3. Value equal to 3 indicates the hybridization is sp2. sp2 hybridization, so boron contains 3 sp2 hybrid orbitals. If the hybridization is sp2, then the geometry will be trigonal planar. Shape depends upon the number of bond pairs and the number of lone pairs. sp2 hybridization indicates 3 orbital. Boron is linked to 3 fluorine. That means all the 3 orbitals are occupied by fluorine. Hence, boron trifluoride has perfect trigonal planar shape. Since it has a regular geometry, the dipole moment is equal to 0. Similarly, if you find the hybridization of SiF4, SiF4, the hybridization if you find by the same method, the hybridization of silicon in SiF4 is sp3. That means silicon contains 4 hybrid orbitals and all the 4 hybrid orbitals are occupied by fluorine. Hence, SiF4 has a perfect tetrahedral shape. Hence, the dipole moment is equal to 0. If you check the option C, that is PCl5, if you find the hybridization by using the same formula, the hybridization of PCl5 is sp3d. If the hybridization is sp3d, then the geometry will be trigonal bipyramidal. Phosphorus is linked to 5 chlorine. That means all the 5 positions will be occupied by chlorine. Hence, PCl5 also has a regular shape. Therefore, the dipole moment of PCl5 is also 0. The fourth option, that is SF4. If you find the hybridization of SF4 by using the formula, the hybridization of sulfur in SF4 is sp3d. sp3d indicates the central atom, the orbitals around the central atom will acquire a trigonal bipyramidal geometry. But sulfur is linked to 4 fluorine. That means out of 5 positions, 4 are occupied by fluorine and 1 contains lone pair of electron. And as discussed, the lone pair always occupies equatorial position. Hence, SF4 has a seesaw shape which is not a regular geometry. Hence, it has a non-zero dipole and the molecule is polar in nature. Now we will discuss on molecular orbital theory concept. According to molecular orbital theory, when 2 atoms combine, the orbitals of the 2 atoms combine to give molecular orbitals. The number of molecular orbitals formed are equal to the atomic orbitals that have combined. Out of the molecular orbitals formed, half are bonding molecular orbitals and other half are anti-bonding molecular orbitals. Bonding molecular orbitals have lower energies and anti-bonding molecular orbitals have higher energies. So this is a molecular orbital energy level for molecules whose atom contains atomic number greater than 7. For example, oxygen molecule. Oxygen atomic number is 8, hence this energy level is applicable for oxygen molecule. Even for fluorine molecule, this energy level is applicable. That is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz. Then pi 2px and pi 2pi both have same energies. Next comes pi star 2px, pi star 2py and sigma star 2pz. So this is the arrangement of molecular orbitals according to their energies. For the molecules whose atom has atomic number equal to 7 or less than 7. For example, nitrogen. Nitrogen atomic number is 7. Carbon, boron, whose atomic number is 6 and 5 respectively. This the energy level is applicable. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px, pi 2py both have same energies. Next comes sigma 2pz, pi star 2px, pi star 2py and sigma star 2pz. The difference between these two energy level is in oxygen molecule or the molecules in which the atom has atomic number greater than 7, sigma to pz has lower energy when compared to pi to px and pi to py, whereas in the case of nitrogen and boron or carbon molecule, the sigma to pz energy is greater than pi to px and pi to py. From this part, we can expect question related to bond order, bond stability and bond length. Bond order can be calculated as half of number of electron in bonding minus the number of electrons in anti-bonding orbitals. For example, calculating the bond order by this formula requires filling up of electrons in all the orbitals. In a question, there will be 4 options. For all the 4, if you try to fill the electrons, it takes time. So there is a simple formula to calculate the bond order for homodiatomic molecules like oxygen, nitrogen, carbon, etc. The formula goes like this. If the number of electrons, if the total number of electrons present with the molecule is greater than 14 and less than 20, then bond order can be calculated as 20 minus n by 2, where n stands for the number of electron, and this is applicable if the number of electrons should be equal to 14 or it should be greater than 14, but it should be less than or equal to 20. If the number of electron is greater than 8 and less than 14, then the bond order can be calculated as n minus 8 divided by 2, where n is the total number of electrons which should be greater than 8 and less than 14. Let's take an example of oxygen molecule only. We had calculated the bond order by using the formula and we obtained the value 2. We'll just try to find by this method. Oxygen contains 16 electrons. Oxygen contains 16 electrons. So n is equal to 16. So this is applicable. So it will be 20 minus 16 by 2. It will be 4 by 2. 4 by 2. The bond order will be equal to 2. Let's take another example. If they ask you to calculate the bond order of O2 plus, O2, oxygen contains 8 electron, another oxygen contains 8 electron, 16, plus indicates deficiency of electron, 1 electron. So the total number of electron present with O2 plus is 15. Again, this formula is applicable. 20 minus 15 by 2. So it is 5 by 2. The bond order will be 2.5. If we take an example of N2 plus, the total number of electron, 7 plus 7, 14, plus indicates deficiency, so it has 13 electrons, so you can follow this formula. So it will be 13 minus 8 by 2, 13 minus 8 by 2, 5 by 2, the bond order will be equal to 2.5. So to calculate the bond order for homodiatomic molecules like oxygen, nitrogen, carbon, you can use these formulas. Students, will move the next question. Which of the following are arranged in increasing order of their bond strength? Bond strength is related to bond order. Bond order indicates the number of bonds that are present between the two atoms. As the bond order increases, the bond strength also increases. Consider a molecule containing bond order 2, another molecule with bond order 3. A molecule with bond order 3 has higher bond strength or higher bond dissociation energy. To answer this question, what we need to do is, we need to find the bond orders of all the molecules and then we should compare it. As the bond order increases, bond strength also increases. We'll try to find out. We'll first take an O2 minus, and bond order can be calculated using the formula 20 minus n by 2 if the value of n is greater than or equal to 14 and less than 20. O2 minus, oxygen contains 8 electron, O2 indicates there are 16 electron, minus indicates you need to add an electron, that means it contains 17 electrons, and according to the formula it will be equal to 20 minus 17 by 2, so that will be equal to 1.5. That is, O2 minus has a bond order equal to 1.5. We'll move with O2. O2 bond order is equal to 20 minus, Oxygen contains 16 electrons, 8 with one oxygen atom, 8 with another oxygen atom. So oxygen molecule contains 16 divided by 2. 4 by 2 is equal to 2. The bond order of oxygen is equal to 2. Next one is O2 plus. Bond order is equal to 20 minus number of electrons that are present. 8 plus 8 16, plus indicates a deficiency, so it has 15 electrons, so 20 by 15 by 2, that will be equal to 2.5. Similarly, the last one, bond order of O2 2 minus, bond order is equal to 20 minus n by 2. O2 2 minus contains 16, 2 minus indicates 2 extra electrons, so it contains 18 electrons, so 20 minus 18 by 2. So this will be equal to 1, 2 by 2, that will be equal to 1. Now, so bond order of O2 minus is 1.5, bond order of O2 is 2, bond order of O2 plus is 2.5, and bond order of O2 2 minus per oxide ion is equal to 1. As the bond order increases, bond strength also increases. So out of the following, the molecule with higher bond strength is O2 plus and the molecule with lower bond strength is O2 2 minus. So in increasing order, I mean lower value to higher bond strength. So lowest is O2 2 minus, next comes O2 minus, next comes O2, and the highest bond strength will be O2 plus. Hence, option B is the right choice for the answer. Students, the next question is, bond stability of H2 plus, H2 minus and H2 are in the order. Bond stability can be predicted by calculating the bond order according to the molecular orbital theory. We need to calculate the bond order of all the three molecules, the species, and then the molecule with highest bond order will have higher stability. Okay, let us calculate the bond order of H2 plus. H2 plus. H2 plus contains 1 electron. Hydrogen contains 1, another hydrogen contains 1, 2, plus indicates a deficiency, hence it contains 1 electron. For such molecules, you need to calculate the bond order by using the formula half of number of electrons in bonding minus the number of electrons in anti-bonding orbitals. Now for this, I can write the molecular orbital configuration as sigma 1s1 because it contains 1 electron. For H2, the number of electrons are 2, hence the electronic configuration will be sigma 1s2. For H2 minus, the number of electrons are 3, hence the electronic configuration is sigma 1s2, sigma star 1s1. To calculate the bond order, you can use the formulas that I had given, 20 minus n by 2 or n minus 8 by 2. If the number of electrons are greater than 8 and less than 14, then only you can use n minus 8 by 2. If the number of electrons are greater than 14 and less than 20, then only you can use 20 minus n by 2. For such molecules or the species, you should write the electronic configuration and then you should calculate the bond orders. For H2 plus, bond order is equal to half of number of electron in bonding minus the number of electrons in anti-bonding. It contains 1 electron in bonding, so hence 1, there are no electrons in anti-bonding, so 1 minus 0, that will be equal to 0.5. For H2, bond order is equal to half of number of electrons in bonding 2, we don't have anti-bonding electrons, so this will be equal to 1. For H2 minus, bond order will be equal to half of number of electron in bonding 2 minus 1 in anti-bonding orbital, so this will be equal to 0.5. Bond stability can be predicted based on the bond order. As the bond order increases, the bond stability also increases. Out of the three species, H2 has highest bond order, hence it is most stable. H2 plus and H2 minus have same bond orders. If the bond orders are same, then the stability is predicted based on the number of electrons that are present in anti-bonding orbitals. As the number of electron in anti-bonding increases, the stability decreases. this should be, you should consider the electrons in antibonding if the bond orders are same. H2 plus has a bond order of 0.5, H2 minus has a bond order of 0.5. So H2 minus contains one electron in antibonding orbital, hence H2 minus is least stable. So if you compare the stability of H2 plus and H2 minus is less stable even though the bond orders are same, because in H2 minus an electron is present in antibonding orbital, so which will provide repulsions. Now, so the stability will be H2, next H2 plus, and the least will be H2 minus. Hence, option C is the right answer.